Young's modulus and energy transfer is our project for Team 3. I am Aiden Davis, and I'm here with Jack Laranjo.
Hello.
So why this experiment? The background is that Young's modulus determines how a material responds to applied stress. And if the applied stress does not exceed the Young's modulus, that means the material will return to its original shape, which is known as elastic behavior. This study investigates how this elastic response relates to energy transfer. Our choice of experiment was bounce height is directly proportional to the energy transferred to the ball using E equals mgh. With constant mass, differences in bounce height linearly reflect differences in energy transfer across surface materials. The application of it, understanding how Young's modulus affects energy transfer even when stresses are well below deformation limits, helps engineers select appropriate materials. This data may apply to everyday products where stresses are often below the deformation limit. So our experiment design, the objective was to measure the bounce height of a tennis ball on 3 surfaces of varying Young's modulus and from 3 different drop heights on those 3 surfaces. The method, we took a tennis ball from a fixed height of 12 inches, 24 inches, and 36 inches, and dropped them onto 3 different surfaces, the surfaces being concrete, plywood, and carpet, and the bounce height for each of those trials was measured, with the response variable being bounce height in inches. The cause and effect diagram, which as you can see is here, the causes were the drop method, the ball characteristics, the environment, how we measured it, the surface type, and the drop height. Some of the important things were obviously the surface type and the drop height. Those are our 2 main factors. But another one I want to mention is the parallax. That is when we were recording with our camera. If it wasn't exactly even with the ball, we could have had some minor errors in our recording of the bounce height. For our hypotheses, we had 3 sets, one for each factor and then one for the interaction of those factors. So we did an ANOVA test, which means we are testing if the mean rebound height is all the same for all the surfaces, if the mean rebound height is the same for all the drop heights, and then the interaction is if the effect of the drop height on rebound height doesn't depend on the surface. Our experiment method, we used the ball packaging that it came in when I bought it, tape and a tape measure. And with this, we construct an apparatus to consistently drop tennis balls from the required same height repeatedly. The ball was dropped onto concrete, carpet, and plywood with 5 trials per surface and per height. Each trial was recorded on camera, so when we were measuring how high the balls bounced, we would go frame by frame on the recording and determine exactly where or how high it had bounced, and that's where the parallax error could have come in. And then we used MATLAB to analyze the variance of the collected data. This is our raw data. Just one thing I want to point out, you can tell that there's a decent difference in each of the height trials. Other than that, it's kind of hard to see the differences. So I'll hand it off to Jack from here.
So from our 2-factor ANOVA test, we can see that there's a incredibly high significance for both the surface and height qualities. It's actually so high that the F value is reported as 0 in the graphs, and we had to go digging through our MATLAB to find the actual values. And the correlation factor between the two of them is 0.02, which is much less than 0.05. So they also interact in that way. Next slide. Cool. Yeah, and so we can just see from this table here, it shows each p-value and each mean difference. It basically tells us that there's a significant difference between the concrete rebounds and the rest of them. So we can see that it rebounds about 0.85 inches higher than the rest. So concrete versus plywood is 0.49, and then carpet versus plywood is not significantly different, but plywood does tend to be higher. Here's our Tukey test. Um, Not sure if I said that right, but it does show us that if we want to maximize bounce height, i.e. the amount of energy transferred, we can choose the stiffest surface, which in our case was concrete, but obviously since this is a relation, it could be any surface in application, and as well as maximizing the drop height or initial energy. Um, and as we can see, the greatest difference is, of course, between the highest drop height and the stiffest surface, and the lowest drop height and the most elastic or plastic surface. By analyzing the actual drop heights, we can use MATLAB to create this graph. It shows us that the ratio between um, rebound height versus drop height significantly drops off actually as drop height increases. However, with the stiffer surfaces, the line never actually crosses, and we could see that the stiffness of the surface significantly improves the rebound height as well. However, at higher stiffness, the difference does diminish. So we have diminishing returns in both um, drop height and in stiffness. As far as our hypotheses conclusions, all p-values were less than 0.05, which means that we rejected all our null hypotheses. That means everything was significant from each individual factor to their interactions. This indicates that the Young's modulus of the balanced surface has a significant effect as well as the initial energy. Um, it is irrefutably evident that harder and less plastic surfaces produce higher rebounds, even at forces significantly lower than that, which would deform them, which is usually what Young's modulus is measuring. Basically, to sum this all up in application terms, even far below the Young's modulus, or even far below the yield stress, the Young's modulus significantly affects energy transfer. And even though adding additional energy does still result in much greater energy being transferred back into the ball upon the bounce, it actually diminishes in its contribution. So a much higher bounce height could only have a fractional difference between a lower bounce height. So what this can be used to in application, if we want to simply maximize the energy transferred and neglect efficiency, we can just choose the most energy possible and the stiffest surface. However, if we want to maximize the efficiency of energy transfer or the percent of energy transferred um, as per the energy supplied, we can minimize the actual energy supplied and maximize the surface stiffness, which will give us the best efficiency. As far as the error goes, we had very limited surface trials, so only 5 bounces per, which is enough to draw reasonable conclusions. Um, but with more data, we can potentially eliminate outliers. We had a very also small sample size, so we only chose or only tested 3 surfaces at 3 heights, which is 9 total combinations, um, which is enough again to produce reliable results. However, it would be interesting to see the effects of more intermittent or more diverse sample sizes. Um, Ball spin or tilt. We couldn't completely eliminate human error, but we did the best we could with what we had, and we did a fairly decent job. However, it was still possible for spin or tilt of the apparatus to play an effect in the measurement um, of the bounces, and obviously minor differences in environmental conditions. Um, each bounce was done with the same ball, This is just to eliminate any variance between tennis balls that could occur. However, that means that also the same tennis ball could um, deform with every bounce. We only did 45 bounces total, which shouldn't, in theory, or shouldn't be enough to actually deform it, but it is possible. And then for future experiments, if we wanted to continue, we could analyze the momentum and impulse analysis. So how um, how much momentum is transferred to the ball versus energy, um, and how long the ball would stay in contact for each surface, which could provide some more insight into the energy transfer. And then another interesting thing that I personally would like to know about is how the effect of the surface temperature um, could affect energy transfer. Whether maybe a hotter surface would be more malleable and thus deform upon hitting the ball or something like that, could be interesting.
And that